order irreversible liquid phase reaction A to B. So these have to be looked into. The first order means the rate of reaction minus of RA would be equal to Kc over bar. C over bar is the concentration of A in the effluent liquid from the CSTR, and irreversible and the liquid phase reaction. So therefore, this F over bar should be equal to this F over bar here. There's no volume change. Um, this occurs inside a constant volume. So this is a constant volume. The value of the volume is also given, isothermal CSTR, with initial steady state conditions as shown. What is the steady state condition? That means the inlet liquid flow rate, of course, which is going to be the same as the outlet liquid flow rate. And the inlet concentration is 2.5 kilomole per meter cube. And the outlet, the effluent concentration is also given. This is under steady state. So what does this tell me? So this problem is to be divided into two sections. In the first section, if you write down the mass balance equation for the component A, that's going to be equal to F over bar CA 0 over bar minus of F over bar CA over bar. That means going out here, minus of course, K P C A over bar, and that's going to be equal to 0. This is that because this is, of course, it's going to be a steady state, right? So if we rearrange this equation, we can find out the value of K, which is going to be equal to F over bar CA over bar 0 minus of CA over bar over KV CA over bar. Once you substitute the values, this particular one comes to be equal to 0.15 our inverse. So that's my first step of this problem. Okay. In the second step, we have to find out the gain of the transfer function relating what? The effluent concentration Ca to the inlet flow rate F. So what we have to find out the gain going to be equal to delta Ca over delta F. That's what we have to find out, right? So this could be found out from two different ways. First, of course, is a perturbation technique. So we give a certain perturbation to the inlet flow rate. Therefore, we can say F is going to be equal to whatever the steady state value plus some perturbations. Let's call this a delta F, and let's say corresponding value of the concentration Ca coming out from here, from the exiting, that would be equal to whatever the steady state value Ca bar plus, of course, delta Ca. Okay. So if we do the perturbation, which we have shown, the details shown in solution, I'll just give the final answer. The G becomes equal to delta Ca over delta F, and that comes to be equal to Ca0 minus of Ca over F over bar plus Kv. And if you substitute the values, this becomes equal to 0.6 kilomole per meter cube, of course, divided by meter cube per hour. Okay, that's first way of doing it. The second way of doing it is a little different way. We can say that let's write down the mass balance equation. F of Ca over bar 0. This is 0. this one right here, 0 minus of F, F, that's what is coming up from here, CA minus of KV, CA, let's say that's at the new steady state. So CA is going to be equal to, of course, CA over bar 0 divided by 1 plus KV over F. It's doing slightly in different way. So delta CA over delta F, okay, which is of course my G. And if I take the limit of delta F tending to 0, that's of course we can say would be equal to the derivative of this thing right over here. And that becomes equal to A over bar 0 to KV over F plus KV whole square. And if you substitute the values, we know the KV and we know the values, okay? Uh, then we can find out that the value of G is going to be equal to 0.6 kilomole per meter cube over meter cube per hour. It's a slightly different way of doing the same problem. Okay, so so this of course is the answer.